So I just want to talk for a few minutes about stereo reconstruction. We're gathering all of this image data from all of these drawers of specimens, and in the process, if we do things with a little bit of forethought and planning, we can solve a lot of problems downstream. And one of them is being able to construct three-dimensional representations of the samples. And so we want to talk about some of our project processes for doing that. We have a lot of these drawers of insects, as you well know. And what we'd like to do is to be able to put them online, which is sort of what the whole center is working on. You know, once you get them online, you have lots of applications you can use them for. Our idea is to be able to create three-dimensional versions of these through stereo reconstruction of multiple images, basically images from multiple angles. So the best algorithm we have to do this is presented at SIGGRAPH, which is the main computer graphics conference each year. The best algorithm to do this came out a couple years ago out of a research lab in Zurich. It's a Walt Disney research laboratory designed for capturing faces. So they're putting a lot of money into capturing actors' faces and making three-dimensional models of an actor's faces. And this is the best method to do it. It takes about half an hour for their algorithm to do this reconstruction. And it mostly finds matching features for multiple cameras, images of a person's face. And it does that at a variety of resolutions, and it's basically aligning the images and looking horizontally for matching features, and then figuring out the disparity along each of those lines to determine depth. And you get this depth, and you do a lot of smoothing in order to get the thing to work out. And so here's an example of it running on an innocent graduate student's face. You know, and you get very noisy data from these things, and so there's a lot of smoothing that has to happen in order for the actual model to get constructed after you do this. And so that smoothing takes a lot of time. It can take as long as 30 minutes to process one of these depth maps. So we're looking at parallel implementations of these things, and we're doing a lot of this work in conjunction with this Intel Illinois Parallelism Center that David and I are a part of as well. And here's some results. You know, from the top view, we've got, you know, this insect specimen. We've taken several images of that, and I think this is just a pair of images and merged it. And it looks pretty good from the top. From the side, you start to see some of the noise, and we're working on smoothing algorithms to reduce that noise. Just a few other results. You know, we're running into the same problems that other people run into. The pins get in the way. And so when we construct a three-dimensional model, we'd like to construct a model that doesn't include the pin, and also the pin will block some of the regions. We have issues with lighting. We want to make sure that when we record these specimens that we do that without harsh spotlights, without direct lighting, so that we're getting diffuse reflections off of the surfaces, but not specular reflections off of the surfaces. And then the nice thing about doing these three-dimensional reconstructions is we need to see the specimens from a variety of viewpoints. If you use something like a gigapan, you're limited to one viewpoint, and you're just, you know, panning the camera across to a lot of regions. If we do something like the CNC machine that David Rayler just talked about, you can have a camera that points down, and you can move it across the image. And the nice thing about having a camera pointing down that's moving is that in the overlap regions from one section to the next, you know, if you set the field of view wide enough on the camera, you'll get an overlap in that region, and so you can see portions of neighboring images in neighboring images. And so that means that if you can't see the label underneath a specimen, you might be able to see it from the view from a neighboring image. And that works fine for ordinary cameras. Unfortunately, the lens we're using is a telecentric lens, which is not a perspective lens. It's an orthographic lens, so it's not giving us any neighboring information from neighboring views. But we also have a pan tilt head on the scanning machine that allows us to rotate the camera so that we can get these other views, both for three-dimensional reconstruction, but also so we can capture the label data underneath some of the specimens that may be included in some of the views. And then we can use the same feature matching software that you use to stitch images together to try to recover those labels from multiple views. And so we're looking at doing that. We also have a bunch of other applications that we want to do to this data once we get it scanned in. This is just another project that one of the other students, Victor Liu, has been working on, which is image matching. He's working on a general problem of finding nearest neighbors in large spaces, high-dimensional spaces. And these spaces can be image spaces as well. And so we've got all this image data of these specimens, and we can start to do image matching in these specimen spaces. And this just happens to be an example, what's called a confusion matrix, where you take a bunch of samples. This is one category of samples. I believe it's ticks. You know, some of the other categories are octopuses and alligators and people and machines and other things in this particular image category. But you can do the same thing for different species of samples, and start to find neighboring images that match, and to see, you know, how similar or dissimilar different species appear just in the image database. And we can start doing things like holding up an insect and see, you know, which images in the database most closely match a given picture of a specimen. And I guess I can show one more thing, is the actual three-dimensional view of one of these insects, which is right here. Just open this up. Try one more thing. So, there we go. So here, this is one of these samples, and once you have it in 3 dimensions, you can start to, you know, rotate around, and you can see some of the, you know, from a side view, you see some of the issues with stereo reconstruction. And part of the problem, it does some of these sections well and some of them not so well. Part of the problem is that the algorithms designed to do this were designed for faces, and faces on the one hand are quite smooth, and also the faces, the resolution of cameras used to capture these faces can capture down to the pore level on the faces, so there's lots of features to match up. When we're dealing with some of these specimens, the surfaces are smooth, or smoother, I should say. And also there's, you know, there's these dark areas that don't have many features. And then you've got these boundaries where they have quite a few features. So we're trying to develop newer versions of these algorithms specifically suited for doing the reconstruction of some of these insect samples that can work with the features we get from those samples. Okay, thanks.